Everyone. Today's session is on first order linear ODEs. Recall that the first order ODE is an ODE where the highest derivative of the unknown function y of x that appears in the equation is the first derivative. But what do we mean by linear? Later in the course, we will define linear differential operators and we'll deduce from that the mathematical definition of a linear ODE. And we will show that in general, an nth order linear ODE is of the following form. So it's an ODE of the following form where we have n plus 1 functions a n till a0 that multiplies y and its derivative, and these are functions of x, and g of x is also a function of x. These functions should be defined on an interval I, which is normally specified. Moreover, the highest the function multiplying the highest derivative a n of x cannot be equal to 0, because if a n of x is equal to 0, then my ODE is no longer nth order, it's of order n minus 1. So from this form we can actually deduce the general form of first order linear ODE, where all the terms before y prime are all 0. So practically a first order linear ODE is of this form, where a1, a0 and g of x are all functions of x. In addition, a1 of x is not equal to 0, because if it is, then it's no longer an ODE, it's a normal equation in y of x. And this linear ODE, since a1 of x is not equal to 0, we can actually divide it by a1 of x to obtain what is called the standard form. So this first order linear ODE is equivalent to the standard form, where p of x is a0 over a1, whereas f of x is g of x over a1 of x. In case the function f of x is equal to 0, then the function, the first order linear ODE, is called homogeneous. And we will start by this equation and this ODE and try to see if we can solve it. We have learned how to solve what we call simple ODEs, or ODEs that can be written as the derivative of some function of y plus a function of x. If we look at this linear homogeneous ODE, at the first glance, well, this does not look like a simple ODE, but if we manipulate it a little bit by actually dividing by y of x, note that we may assume that y of x is not equal to 0, because we know already that y of x equal to 0 is a solution, it's a trivial solution. So what we want to find is non-trivial solutions. So we may assume that y of x is not equal to 0, and we may divide the ODE by y of x to obtain the following form. Now, note that the first term is only a term in y, the second term is a function of x, p of x, and you should recall that y prime of x over y of x is nothing but the derivative of ln of absolute value of y of x. Recall that from Math 201. So now we obtain what we call the simple ODE, and we can actually integrate this ODE. We know that the antiderivative of the first term in here is nothing but ln y of x. We have we know that the antiderivative of 0 is a constant, some constant c. As for the antiderivative of the function p of x, then this will depend on what the function p of x is. So for example, if p of x is x, then its antiderivative is x squared over 2. If it is cosine x, then the antiderivative will be sine x. If it is 1 over x, then the antiderivative will be ln of absolute value of x, and so on. So note that this denotes the antiderivative of the function p of x. And if we we move all the terms not containing y of x on one side, then we can take the exponential of this equation. We can take e of the left hand side, which will give us absolute value of y of x, and we will get e to the power of c minus the antiderivative of p of x. Given our knowledge of the exponential function, we know that e to the alpha plus beta is nothing but e to the alpha times e to the beta, so we get the following form. And the last step would be to remove the absolute value, and we can then deduce that the solution of the linear homogeneous first order ODE is y of x, which is equal to a constant c times e to the minus the antiderivative of the function p of x. Now, as an exercise, you may check at home that this function is actually a solution of the ODE that we started with, and note that the derivative of the exponential of a function is nothing but the derivative of the function times the exponential term. Okay, so now we know how to solve linear homogeneous ODE. We're able to integrate it and get a solution. But what if my function f of x was not equal to 0 and my ODE was not homogeneous? So what can I do? Can I still do the same procedure whereby I can integrate my ODE? So we're gonna take a look at a specific first order inhomogeneous linear ODE. So look at this ODE. We have the left hand side and the right hand side. Now note that on the left hand side we have x squared multiplying y prime, and we have 2x multiplying y. And note that 2x is nothing but the derivative of x squared, whereas y prime is the derivative of y. So this looks like, if you recall, the product rule of differentiation. So practically this is nothing but the derivative of x squared times y of x. So in this case, we can actually apply the same integration method that we did for the previous example, whereby we find the antiderivative of this term, which happens to be x squared times y, whereas the antiderivative of x squared is x cubed over 3 plus some constant c. Do not forget the constant c. And finally, we can deduce that y of x is x over 3 plus c over x squared. So in here we were lucky because our left hand side was actually equal to the derivative of some function of y. But is this always true? So can we always write any linear inhomogeneous ODE as a derivative of some function of y equals to a function of x? Now look at this ODE. Let's take the following ODE. In here we have y prime of x plus 2x, y of x equals to x. So one thing to note is that my left hand side in here, 2x is not the derivative of 1. Y prime is the derivative of y, okay, but 2x is not the derivative of 1. So I cannot write it as we did in the previous example as the derivative of a function of y. So the question is, can I transform it into an integrable ODE? Can I do so? So one way to transform my ODE into an integrable one is to multiply it by some function of x. So the goal is to multiply this ODE by some function of x where this function of x should satisfy the following. Note that the function of x, its derivative should be equal to 2x times the function itself. In order so that I can write my left hand side as the product, as the derivative of some function of y. An educated guess in this case would be that I can multiply my ODE by a function which is in this case e to the power x squared, because the derivative of e to the power x squared is 2x times e to the power x squared. So if I do so, if I multiply my ODE by e to the x squared, I get the following equivalent ODE, and in this case my left hand side can be written is nothing actually but the derivative of ex squared times yx, and now we can integrate the ODE and find the antiderivative. The antiderivative of the first term is nothing but ex squared times y of x, and the antiderivative of my right hand side is e to the power x squared over 2 plus some constant c. And the final step would be to deduce the general form of yx, which is half plus a constant c times e to the minus x squared. So what we can deduce is that given any linear inhomogeneous ODE, we can transform it into an integrable one by multiplying it by some function that we call the integrating factor. So e to the power x squared in here is called the integrating factor. So we can multiply our ODE, whatever this ODE is, by some integrating factor that would transform my ODE into an integrable one, or a simple ODE. Now the question is, in here we were lucky because we were able to guess what this integrating factor is, but this might not be easy for other linear first order ODEs. So the first question is, how can we find this integrating factor for any given first order linear ODE? This question will be answered in the next session.